So 605 can place flowers. You have a long flower bed in which some of the plots are planted and some are not. So we have a straight line, plots of land inside, some are empty, some are already flowers, and we want to place new flowers. We can only place new flowers in an empty plot of land. So only those empty plots of land can be used for placing new flowers. Seems logical. However, there's additional constraint. Flowers cannot be placed in adjacent plots. So it's not only an empty plot of land that we need, we also need to check its neighbors. So its previous plot, current plot, and the next one. All three in such a window of plots have to be all empty for us to be able to place a new flower. And then given an integer array, flower bed containing zeros and ones, where 0 means empty and 1 means not empty. So 1 means flower, means that flower is already there, and 0 means an empty. And it's an integer array, so it's a linear structure, the easiest thing that we could get. And even easier, those are just integers, and the additional constraint on the integers are that we only get ones and zeros. And so not many options that we have. We have a binary input in that case. And the next thing is an integer n. So two things that we are given as an input, those the data structure, that container, that array of plots of land, which tells us how the current situation in the flower bed looks like. And the second is n. And what is this n? This n is just a number, but what does it mean? Return true if n new flowers can be planted in the flower bed without violating the no adjacent flowers rule, and false otherwise. So we already see also that output is a Boolean, either true or false. We don't have to return any number. We just need to say if we can put n new flowers, if we can place n new flowers. So if there's enough empty plots of land for us to place those flowers, then we return true, and false otherwise. And let's take a look at the examples. So first we have flower bed, which looks like this: 1 flower at the beginning, then 0, 0, 0, 3 empty plots of land, and 1 at the end. And they ask us if the n is equal to 1. So if we can place 1 additional flower here, is there a place in which I can put it? Yes, here in the middle. I already can see it. It's an easy example, just 5 elements. I have the sequence of 3 empty plots of land, and I can use the one in the middle to place a new flower. There is no other space for me, because here, for example, if I wanted to place it here, I cannot, because there's already 1 flower to the left, and the same here, there's already 1 flower to the right. So I can put exactly 1 new flower in the middle, and that means that the output is true, because 1 is greater or equal to 1. And so I can put at least 1 flower here. But if we increase our number n to 2, and the flower bed stays the same, the output is false, because I cannot put more than 1 now. So 1 is less than n. This one is impossible. Let's try to draw it to see how I think about it, and how can we implement an algorithm to check this for us. So let's make it a bit bigger so everyone can see. And I need plots of land. So this is my plot of land. I need 5 of them. 1, 2, 3, 4, and 5. Like this. Should be good. And now I need to place flowers. So I would like to distinguish between an existing flower and a new flower placed by my algorithm. An existing flower will be green. We have 2 existing flowers at the very beginning and 3 empty places. Yeah? So empty places stay like this. I think that's a good visualization for an empty place. And now comes our algorithm. So what can we do? We can go through each element. We can iterate over our array. We can create a loop, and inside the loop, we have to do what? We have to take 3 consecutive elements. We have to create a window in which we will check previous, current, and next. And if all of them are empty, I can place a new flower. That's it. So every time I have to take care of 3 elements at the same time. Here, first, let's start from here. Oh, what's happening here? Let's think about it, but let's write it down just in a second. But for now, we have a case where already at the first index, already at the first element is a flower. So for sure, I cannot place my flower here. Then I slide to the right, and those are my 3 elements. So first is an existing flower, and then to empty. Can I place it here? No, because one of those 3 is already taken. Can I place it here? Yes. So let's change maybe like this. This one is placed. And how to mark it? We need to introduce additional variable. So everything new we introduce, we mark it as bool. And first we would initialize it with 0, but every flower we put, we increment it by 1. So now we incremented it, and it's equal to 1. In the end, we will ask, is total greater or equal to n? And if the answer is yes, we return true. If the answer is false, we return false. If the answer is no, we return false. Yeah. And so in that case, we can continue our iteration, but also we can exit empty because we already know that total is greater or equal to n. So we can close our iteration and return an answer. Our answer is a green mark. Yes, that's great. Let's copy all of that. That can stay. And let's do the same thing for the example 2. That example 2 is the same thing, just n is equal to 2. And what did we say at the end? Total is 1. Is 1 greater or equal to 2? No. That means that we return false. Sorry. I didn't want to change everything. Not to confuse you, not to introduce too many colors. That's just my output. So here is how I imagine the algorithm, what is going on inside our program. Here is the additional variable that I introduced. And besides it, also we were talking about the windows. So we need previous, we need current, and we need next. And here at the end are our answers, so the output. We can already start. So let's implement our solution. Have to write it in terms of a class called solution. It was here before, like before they give you this skeleton of an answer, but of course I implemented it before the video and now removed it to not get distracted and be able to do it from scratch. So you can follow my thought process. And the method inside the class is called can place flowers, like the title. And it's a camel case. I think that's the standard for Leetcode. We have 2 inputs, flowerbed and n. So what did we discuss about? We have a total which tracks how many flowers we have already planted, and we have a window of previous, current, and next that we are sliding through as we are iterating through our flower bed. And by the end, we compare total with n, and if total is greater or equal to n, we can we return true, and otherwise we return false. So we can just return this condition, and this would suffice. And here we can, of course, iterate through every element inside flowerbed like that in Python, into simple loop, and it would go through each one of them. But we want this window. We want previous, current, and next. So what could we do instead is here put the last one, next, and start from the third element like that. And before we enter the loop, we can check the current. We can initialize the current to the second element and the previous to the first element. So those we initialize explicitly, and inside the loop we will be sliding. So every time we move to the right side, we put the current as a previous and next as a current, and the next itself will be changed through the loop itself. And we have, of course, one if. What was our if? Our if was all three of those are zeros. So if previous is 0 and current is 0, double equal sign, and next is 0, then what? Then we are planting our flower. How are we planting it? We are increasing the total by 1, incrementing by 1, and we are planting it on the position of the current. Yeah? So we check if two neighbors are empty and current is empty, we can put it on the current. So current becomes 1. Here's 1. And we are sliding, so previous becomes current. Current becomes next. And that's it. And next is moved just through the loop itself. So if we check right now, if we didn't make any mistakes in names or any syntax errors, then we should at least have correct those two test cases that we discussed already. And this is indeed the case. And now we can run through all the test cases, which is like over 100. And we can see that it already found that we haven't satisfied all the edge cases. So what's going on here? Maybe first let us put it here and continue our great tradition. So this here of fuck. Why is this so stupid? Now it works good. So that's our flower bed. That's our n is equal to 1. And that's what I like. Let's try to draw it. So we still have 5 elements. Perfect. But the flowers or the original flowers are on different places. So here we have 0, 0, empty, empty, 1, flower here, empty, and flower. And n is equal to 1, and it tells me that our algorithm returned false, but it should be true. So where can we put, sorry about that, new flower? It looks like we can put it here. So there is one edge case which we didn't handle. The flowers at the beginning and at the end can be put if just first 2 elements are empty, and of course like this element out of existence outside of our original array, we assume that there is no flowers there, so it also can be planted here. So for the first element, we just need to check the second one, and if both of them are empty, we return true. And the same thing would hold for the end, so we would check the last 2 ones, and if those are empty, we can also return true. And it looks like our current algorithm is not handling that case. So what we could do to not add any special ifs is to extend the original flower bed with 2 padded empty spaces, which always are empty because, as we said, those space outside of our flower bed, there are no flowers there, so we can always place a new flower here if it's an empty place and if next place is also empty. So how can we extend it? That would be an easy correction, and let's see if it handles all the cases. We just add 2 zeros, but it could be expensive one because we are inserting at the beginning of an array, so it could be quite expensive. We can see we can see soon how it compares to the result. And let's submit again and see if it helped. So we've already handled all the cases. We are even quite fast. So we beat 86% of our competitors when it comes to the runtime, and when it comes to the memory, we beat 50%. So we could probably use less additional memory, but we didn't really use that much. We just used previous, current, and next, and total. So 4 variables, which is strange, but okay. So for that, I don't know how to expand it, but this could be handled without modifying the original array, and maybe it would. Maybe this would also have the memory, but for sure could be also better for the runtime because it takes some time to insert those. Yeah, okay, but I can say that we are satisfied with those results. And if you have a better approach, you can write down in the comments.